All right, welcome back, everyone. Let's go ahead and take a look at the main result in really all of inferential statistics. So in the previous video, we basically stated that we will be doing three things, and that is understanding how samples behave to obtain a point estimate, an interval, and finally perform hypothesis tests. All of that, really all of those pieces in inferential statistics depend on this one result. And this result is known as the central limit theorem. And the central limit theorem essentially tells you when you compute a mean, a sample mean, then I know how that sample mean behaves. So let's go ahead and just take a look at what the theorem says, and then we'll observe examples of that theorem. So the central limit theorem allows us to describe how sample means will behave. And the theorem basically says let x1, x2, and xn be a random sample from a distribution. And the most important part is that it's from any distribution. So if you take a look at this, they're basically saying, here's your first observation, x1. Notice that it's random variable x1, and that means that it's an ordered list, but the order of it doesn't really matter. So here you have, so here you can see we have our random variable. And when you go ahead and take a sample, you're going to value like x1, a value like x2, then x3, and so on until you get xn. So from this parent distribution, let me emphasize that. So this result basically assumes that you know the distribution. So notice that from the population distribution, we're saying we know mu and we know sigma. And so this is a very unrealistic assumption, but let's just go ahead and say, let's pretend that we know the population. And my goal simply is to understand how the sample means behave. So if this is the population, I can go ahead and say, well, from that sample, I will compute a specific sample mean. And that's this sample mean right here from that first sample. And now if I go ahead and repeat that, so notice I went ahead and now I got my sample mean, x bar, the blue one. And then you just repeat it over and over again. Notice that we've already done this. We did this when in our lab, when we looked at the number of the length of the words in the Gettysburg Address. So it's a process that we're actually very familiar with. We take a simple random sample and then just place a dot, and that dot represents the sample mean. Take another sample, you're going to get another dot, and that dot would represent a second sample mean. And you continue that until you get enough of a pattern. And now here is what the central limit theorem states. All right, so the central limit theorem says that the expectation of the sample mean. So now we have a new random variable. The random variable, we're going to write it as capital X bar. Notice that is different from capital X. Capital X is the quantity of interest. Capital X bar represents the random variable of the sample mean. And so here we can see that the expectation, so first result, is that the expectation of the sample mean is simply mu of X bar. That's basically the same thing. So notationally, these are equivalent. And that is the population mean. So here in the sampling distribution, let me write it out. Let's write it in pink. So if we take a look at the sampling distribution here, it says that this center mu of X bar is the same as mu. So therefore, they went ahead and used the same symbol. So mu of X bar represents the center of the sample mean. So here is result number one. And it simply says the center, so that's mu, of the sample mean equals the population mean. So if you say that out loud, it basically tells you that when you take samples and compute the sample mean, that the center of those sample means will be the same as the center of the population. Result number two says that the variance of X bar, which if you recall, the variance is the square of the standard deviation. Then again, notationally, this first equality is the same. So the variance of the sample mean is the same as the is written as sigma of x bar, because that's the random variable of interest, squared. And this one's kind of interesting because now it says that the variance of the sample mean is equal to the variance of the population, that's sigma squared, divided by the sample size. So therefore, if you go ahead and take the square root on both sides, you'll get that sigma of x bar, so the spread or the variability of the sample mean, is equal to, again, take square root on both sides, is equal to the square root of variance squared over n. So if we simplify that a little bit, that becomes, so square root of sigma squared over square root of n, which is sigma over square root of n. So the end result is that the spread, so note, let me annotate this. So let's note here, our population has this amount of spread, but then when you take a sample of size n, the spread decreases because it's the same sigma, but you're dividing by square root of n, which is the sample size. So therefore, the variability decreases proportionate to the inverse of the sample size, the square root of the sample size. So if we take a large enough sample size, there will not be a lot of variability. So this is the last part that's missing. So we know the center now, and we know the spread of the sample mean. And now the last part is very important. So we know the center, we know the spread. Notice this is really true no matter what. The center will always be given by this formula, and the variability will always be given by this formula. But the most crucial part, the part that's missing, because if you remember in our preview, we said if we have a named random variable, then we can find probabilities. So far, I cannot find probabilities because all I know is the center and the spread of the data set. I don't really know its overall behavior. I simply know the location of the data set. And so this last part is very important for us. It basically says, if your sample size is large enough, then the distribution of the sample means is approximately normal. So let's go ahead and simulate this. Let's see this in action. This is going to be a simulation, so please do it with me. And what I'm going to do is, if you download the PDF, you can click on this. It's Log5Stats website. And what I want you to do is I want you to select the data set that says Hollywood movie 3rd edition budget. So I already clicked on it. So let's go ahead and click on this. And then up here, you can click Hollywood movies right here, 3rd edition budget. So it's an applet from a different textbook. And what I want to point out is that you have the population here given. So remember, in most cases, we don't know the population, but for example, movie budgets, that's something that we can work hard to kind of track as the year goes on. And then at the end of that, we have an actual population info for the budget of all movies for that specific year. So if I click on show data table, you'll actually see the table of all of the movies that they are discussing. So you can see here that we have, for example, 21 Jump Street with a budget of 42 million. Another one, for example, Battleship with 220 million, Brave with 185 million, and so on. So you can see that these are all the movies that from some year, I'm not quite sure, or maybe several years. All right, so anyway, let's go ahead and call, oh, look, Despicable Me 3 with 75 million. Wow. All right, so let's close this. And so this is your population. There are 1,056 movies. The mean is 51.379. Median is 30. Standard deviation is 57.927. So I went ahead and actually screenshot that and included that in our notes. So let's quickly go ahead and label. Let's emphasize that we have, in this example, we have the population. And that's a very strong assumption. So for now, don't worry about it. Just say, if that is the population, that's the population. We're not going to question it. So really, really important that we understand that's the population. And let's note that the population is actually skewed right. You can see that from the histogram that they produced here. All right. And now Based on the information that's given, my population size is 1,056. The population mean, mu, is 51.379. And the population standard deviation, so that's sigma, is equal to 57.927. Given this information, we now know how samples from this population will behave if I compute the sample mean. And this is basically the graphic that I have up here. So given population information, the claim, according to this theorem, is that I can tell you how the sample means are going to behave. And notice that this is a random sample. So it's very, very important that you recognize. We are now making a very bold statement and saying, I know how the sample mean is going to behave. Okay, so let's go ahead and try this. Let's take samples of size 10. So here's my population, and I'm going to leave this at 10. So let's type in 10 right there. And then I'm simply going to take a single sample. So let's generate one sample. I'm going to generate one sample so that you can see this. And then here is your sample information. So you can see where it says sample, it tells you show table. So they went ahead and took a simple random sample of 10 movies without replacement. And we can observe here that this is the sample that we found. So we got the movie I'm Not Ashamed, Overboard, The Mummy, We Are Friends, Ant-Man and the Wasp, Every Day, The Raven, Wonder Woman, White Boy Rick, and Escape from Planet Earth. We've got the budget right here on the right-hand side. And then what they went ahead and computed the average for that. So that one sample, you can see here's the sample distribution. You can observe all of those budgets that are in our sample. And here is the sample mean, 59.2. So I go ahead and represent that with a single dot of 59.2. If I go ahead and take another sample, obviously I'm going to get a different statistic because of natural variability. And you can go ahead and just see the sample that you got there. So here I got Avengers Infinity War. That's a very popular movie. Lots of money that was spent on that, but it also made a lot of money. So it makes a lot of sense that they spent a lot of money. So anyway, here is the sample mean for that. It's 77.36. And now this two observations is not enough to determine a behavior, a pattern. But you can see that if I repeat this many, many times, I start to observe a certain pattern. So let me sample this so that I can even this out to 100. There it is. So I have 100 samples right now. And this doesn't really look like any sample. So let's go ahead and sample 1,000 times. Let's click this. And then let's go ahead and sample another 1,000 times. So click this. You can go ahead and just generate as many as you want. Try not to click it too quickly because it'll slow down the program in the background. So now what I want to point out is that if I generate enough samples, remember that every single dot that you observe here. So for example, let's say you select a dot right here. That represents a sample mean. And the sample mean is somewhere around 90, just looking at the value right there. So here are the sample means. Now, luckily, they actually have the statistics of interest right here. I've got the number of samples and I've got the mean of the sample means. So notice this is the center of the sample means. And according to this, we're going to write this as mu of x bar because it's the center of the sample means. And this is a simulation that we see here. I went ahead and simulated 5,100 random samples and computed their center. And look at that center. That center is 51.270. Now, the standard error, there's a reason why it's called standard error. We'll talk about that later. So here, the standard error is actually the spread or the variability of the sample means. And symbolically, we're going to go ahead and write that as sigma of x bar. So again, sigma represents standard deviation. So this is the standard deviation of the sample means, and I'm simply going to write that as 18.118. Now, something very important here happened. Look at these values that I got. And what I'm going to go ahead and do is I'm going to go back to our notes and actually compute the, work with the formulas. Before I do that, let's just go ahead and take a note of the shape that we observe here. The shape that I observe looks very symmetrical right up until here, but then it keeps going to the right-hand side. So you can see that this actually is slightly skewed right. So anyway, before I do this, let's go ahead and go back to the notes. So here in the notes, let's go ahead and pretend that we did not simulate. So now we're predicting the future. If I go ahead and simply take a look at my population and I compute the mean according to the formulas, so by central limit theorem, with sample size n is 10, if we go up and revisit the formulas, we observe that formula number 1 says I can tell you the center. The center of your sample means, your distribution, will be the same as the population center, mu. And my population center is in green. It's 51.379. Now, let's note how in this simulation, when I simulated it to make these notes, I simulated 3,000 random samples, and I got a value of mu of x bar of 50.985. And that's pretty close to 51. You can see that the population mean was 51.37. In this simulation that I have, my sample mean is 51.270. So the mean of the sample means is 51.27. So notice how that's very close to 51.379. And obviously it has to do with randomness, but I'm predicting how that randomness will behave. So I basically got a pretty good idea of what this center was going to be, even before doing this, because we are essentially invoking the central limit theorem. So let's go ahead and just take a look at the variability. What about the variability? Variability, remember, is difficult to predict. It's also very difficult to compute because it's a lengthy computation. But central limit theorem, really one of like the pinnacles of statistics, states that the spread, the variability in this sample here, in this simulation, is going to be given by the formula. You can see it right here. So the spread of the sample means will be given by sigma over square root of n. And this means something. Remember, sigma is the population information, and it's right here in green. So that's 57.927. And I'm going to go ahead and divide that by the square root of my sample size, which is 10. All right, now go ahead and throw that into a calculator, for example, Desmos Scientific, and you will get the value 18.318. Now, let me go ahead and compare that. Again, this is a prediction. In red, I'm predicting only from knowing the population. Take a look at the standard error that I obtained in the simulation that I did with you. So that was 18.1. The predicted standard error was 18.318. So I'm very, very close. And if you take a look at this, when I did this simulation, the standard error is 18.249, so closer still. So in this simulation, that's on your notes, the standard error is very close. This mean is not very close, but again, close enough. And when I did it with you, you can see that the sample, that the center of the sample means is a lot closer to the prediction. And that's the power of the central limit theorem. So 1 and 2 always apply. No matter what sample size you get, this will always be true. And 3 will take a little bit of care that if the sample size is large, our distribution will be approximately normal. So that is something that I want to mention here. My sample size of 10 in this case is not very large. And that's what's responsible for the fact that my sample, sampling distribution here, please remember that sampling distribution is the distribution of sample means. We've already talked about that. So that's the distribution of the sample means. But this distribution, you can see that the shape is actually slightly skewed. And the reason why that's actually skewed right is because our population was skewed right. So if your shape is not, if your sample size is not big enough, then the shape of the sampling distribution is inherited from the parent population. So again, slightly skewed because it inherits the shape because our sample size is small. Sample size of 10, that's not big enough. So let's go ahead and do this again for a bigger sample size. So let me go ahead and just simulate this real quick. Let me change this 10 to, for example, a 20. Press OK. And let's just simulate a few of these. Maybe let's go up to 5,000. And you can see that now it's slightly more symmetric. If you were to compare this, I should have probably drawn on this. So let me try it. So it looks like this is the distribution. All right, and let me set this back to 10. All right, and here is the distribution. So that right there is for n is 10. This right here is n is 20. And notice how both of them are actually still slightly skewed. So let's go ahead and set this, for example, to 30. And in each case, I'm just simply doing 5,000 random samples. All right, so there's this one. So we're at 30 now. Let me draw this. Uh-oh. So this right here in red is 30. Let's do this one more time. Remember, because they just simply said our sample size has to be big enough. The theorem doesn't actually tell you what big enough means. So that's a problem. And this is all proven mathematically. So if you're wondering why, it's a limit argument. So if you're taking calculus and you know what limits are, that's the reason why they don't tell you. They just say in the limit, this will be true. All right, and this is 5,000 samples of size 40. So now let's go ahead and take a look at the shape. All right, let's go ahead and clear this. So let's put sample of 60. Okay. All right, and you can go ahead and sample this, but if you simply look at these curves, you can see that the pink ones, 10, 20, are definitely skewed to the right. By the time I look at 30 and 40, the distributions are less skewed. By the time I get to 40, it's very, very symmetric. So maybe let me try 60. Oh, wow. All right, so if you take samples of size 60, we can observe now that my sample is very, very symmetric at this point. All right, so just to get rid of that, so we can observe that as the sample size increases, yes, the distribution does tend to look more normal, but the big takeaway for us will be, what does big enough mean? And so for this class, it's just a rule of thumb. There was nothing very scientific about this. I just simply went ahead and observed it. And so you were witness to this, that by the time I got to a big enough size, for example, 40, that the distribution does more or less follow this normal curve. So what we're going to go ahead and say is we're going to say if my sample size is greater than or equal to 30, then the random variable x bar will be normal. So it's approximately normal. That was good enough for us. So our book will use the sample size of 30. Other books might use sample size of 60 and 40, and I hope it's clear why. It's just that somebody decided that that was going to be the value that they want. All right, let's go ahead and end this video here, and I want you to go ahead and notice that here we simulated with sample size 40, and I want you to just practice this. If this was your sample size of 40, here is your mu of x bar, predicted, actual simulation, and here is your sigma of x bar, actual simulation. What I want you to do is I want you to tell me, according to central limit theorem, what is the predicted center, and then what is the predicted spread? So go ahead and take a look at the example that we did before and find those quantities. All right, thank you for joining me. In the next example, we'll continue with more on this.